Right. I know that during the lectures we actually have very little time for me to do as much as I would like to do in the class. And what I thought I might do now is to just spend some time, just put up these sort of web videos as I kind of work through, particularly I think with the weekly tests, where I can at least go through all these questions which we've asked. And hopefully this will also help you guys just to start to feel, well, start to just get a better sense of what's going on in this chemistry. As I said to you, I know it's difficult in the beginning to start to make sense with this chemistry which you've left behind quite a bit. I'm going to work from the weekly tests. Unfortunately, I can't get this a bit much bigger, well, any bigger than I have it at the moment. So it's probably going to help if you have the test in front of you so you can see things in case some of it's a bit unclear. But anyway, the first question over here, I know some people would have had kind of a bit of a struggle with naming, RNS and all that sort of thing. On the whole, I think you guys got it. You remembered the basic rules, and so I don't want to really spend too much time on this. If you got it wrong, then just go and have a look at it again. I think you'll very quickly see, oh yeah, okay, I see exactly where I went wrong. And if you've got a problem, just come and speak to me. It's not like we are specifically going to be testing this in the exams, but it is something that you should know, and in terms of chirality. All right, question 2. You see, this sort of question is quite important because I put in a whole lot of different mechanisms on purpose to try and see if you can recognize when something is a good mechanism and it can work, and when something is bad and it can't. And each of these mechanisms is actually an important one which you've either seen before or you should know. So just take this one over here. I'm going to redraw it a little larger so that we can just see what I was explaining there. This is the classic E1 conjugate base elimination sequence. It's the last step in this sort of reaction. And essentially, this is what I'd shown, is that the lone pair of electrons donates and forms a pi bond over there. This pi bond shifts across, and in so doing, something has to break. A bond has to break. And it's okay. The OH can leave, although generally a bad leaving group. Once that happens, it's actually okay, and we don't have to worry too much. So the product we get looks like this. It's an alpha-beta unsaturated ketone. All right, so that sort of mechanism is perfectly acceptable and is correct. Option C was related a little bit more to what we've been doing in this course, and that is taking an enolate, but the difference here is that the enolate is reacting with a acid chloride, in this case acetyl chloride, and the mechanism I drew over there showed the minus attacking the carbonyl, carbon, and then the pi bond breaking, which is of course correct. That's a normal sort of flow of electrons when we add the negative charge to a carbon that has has sp2 hybridized and has a pi bond on it, that the pi bond will break first. Once that has happened, then yes, the leaving group will leave, and what we will get, so this is the first intermediate, O minus, CH3, and a Cl. And now what will happen is the negative charge comes back in and the chlorine is given off, and so we've effectively acylated, because we put an acyl group onto the oxygen. There's a bit more. This is the acyl group there. There's a bit more to this question than meets the eye. The one thing is just a very subtle thing we don't see a lot in this chemistry, but the enolate chemistry is that the oxygen is the hard nucleophile, and actually for acid chlorides, like this functional group, that is the preferred mode of attack. Almost all the other examples we see are going to be the enolate adding to some sort of electrophile, except with acid chlorides and with the silyl chloride, silicon chlorine bonds, which are also very hard, and they'll add that way. All right, so that mechanism was also correct. This one over here is another mechanism which we're going to become very familiar with. It is the enolate, all right, adding to an aldehyde. It is an aldol type of reaction. In fact, this particular mechanism, we'll be dealing with it. You would have done this, in fact, I think you did do this last year. We've done this in a prac, and I did this with you. And the net product of this, so the enolate goes down, the pi bond of the enolate breaks and adds as a nucleophile to the carbonyl group of the aldehyde, which is a very good electrophile. And the pi bond breaks, and so we connect all of that together. There's carbon, new bond, going to this carbon, which has an oxygen on it, and there are the other bonds, and of course the O is now minus. But the minus can be protonated, and if we follow this through, actually this and this are related to each other. Try and think about how you could go from there to something that eliminates to that. We're going to be doing that as well. And then the mechanism that doesn't happen then, I mean, all three of those work. What doesn't work is this one over here, which shows you, let me just draw it out again. We have something that looks like this, and I've got 3 hydrogens there, and then we have an OH minus, and what I showed over there was these pi electrons breaking like that, sigma bonds breaking and going towards the oxygen. There is so much wrong with this sort of picture that it really isn't, it's hardly worth even describing this. Electrons moving from a pi bond away from an oxygen like that means that the oxygen is actually going to be deficient of all its electrons. At the moment it has its octet. You take electrons away from the oxygen, it's going to be left with 6 electrons. It's not stable, it doesn't exist. A carbon-hydrogen bond breaking where the electrons are going with the hydrogen to something is also a big no-no. All right, that's an H minus being kicked off. It is a horrible, horrible leaving group, and it just doesn't happen. And then, of course, the H minus taking its electrons and giving it to an oxygen which already has its octet fulfilled. All right, this oxygen already has 8 electrons around it. Now something's giving more electrons to it. This just does not happen. If anything, the sequence of errors with those reagents would have been something a lot in the completely the opposite sense, and would have looked obviously more like this, forming the enolate. All right. Okay, so that was that question. The next one was again also, mechanisms that were, were they correct or were they not? I gave you an example of triphenylphosphine adding to an alpha halo carbonyl compound. All right, this is methyl bromoacetate. All right, it's the methyl ester of bromoacetic acid. Draw that out if you're not sure. And what I showed was the lone pair of electrons on the phosphorus acting as a nucleophile, adding to the carbon that has the leaving group on it. And we've learned that actually a carbon with a leaving group on it that is alpha to a carbonyl is actually a very reactive electrophile. And so this reaction occurs very, very readily. And so we would end up with something that looked like this. We still got the 3 phenyl groups. Phosphorus is actually now positively charged, and we have a Br minus being given off. It's a kind of Wittig reaction. I'm not sure whether you've done that yet. If you did that last year, or you will be doing it this year, but look out for that. That is you're going to see examples of this. Phosphorus is just below nitrogen. It has lone pairs of electrons. It reacts like nitrogen. Think of it like that. But phosphorus is still different. It's big, and it can have a lot more other bonds to it. So that reaction was correct. This option C over here is, in fact, part of the mechanism for the formation of an imine. And so let me just draw this out, OH2. All right, so the oxygen was OH, it's been protonated to make OH2, it's a good leaving group, and all we need to do is kick in with a lone pair of electrons, and that kicks out. That's what I've drawn out. This is a good movement of electrons and will occur. And the product would look something like that. We've got OH2 that left, and we still have the hydrogen, so we'll include it, but the next step would be that the hydrogen would leave. The water could pick that up, and then we'd have the neutral imine. This is the iminium. And the imine is without the H. All right, so that one was correct as well. Then we had what is called, I did this mechanism over here, H2N, just another ethyl group, just a random one, and I showed this, the nitrogen attacking this carbonyl, and that breaking like that. Now this is again a very normal mechanism. It's a nucleophile, which is busy adding to a carbonyl, which is very electrophilic. All right, a nucleophile adds, the pi bond breaks. It's actually very standard. This is actually the start of the mechanism of what's called an aminolysis. All right, aminolysis, because if we used water, if this was OH2, it would be hydrolysis of an ester, and this is breaking the ester, lysis, with an amine, aminolysis. All right, and the net product of this, I'll just draw out the first intermediate, but the net product of this is an amide. And just notice that the nitrogen is positively charged because we're two hydrogens there. All right, and so the next step is this can kick back in, kick out the methoxy. Methoxy can pick up the H, and we end up with the amide plus the methanol. All right, so that was also okay. And then let's move this down. This one did fox some of you because you saw the acetate, O minus, going to a nitrogen that was positively charged, and it had 4 hydrogens on it and a CH3. And I showed this movement of electrons, the negative going to the positive, like that, and I also showed the H leaving. And so now what's wrong with this is don't ever think of a nitrogen with a positive charge on it as an electrophile. All right, it doesn't want to accept any more bonds, and if something's going to leave, something like this, that's leaving is H minus. It's a very, very bad leaving group, and this is not going to happen. All right, so this was an incorrect answer to that question. Hopefully that makes sense to you. All right, question 4, you had to place the following species in order of increasing reactivity as leaving group. And so what you had to remember was that a good leaving group, all right, and of the leaving groups we had NH2 minus. A good leaving group is the conjugate base of a strong acid. And so if we look at these options that we have there, the acid of this would be acetic acid, the acid of this would be water, the acid of this would be ammonia, and the acid of this would be the hydronium or hydroxide, H3O+. All right. And so looking at each of these, deciding which is the strongest and which is you're looking for as a leaving group, which would have been the strongest acid, because the strongest acid means that these, as conjugate bases, that one would be the best leaving group. Well, the worst leaving group must be this over here. An N minus is a very unstable species. Its conjugate acid is ammonia, and ammonia is not an acid in any stretch of the imagination. To remove that proton, there's a pKa of about 40, and that's just not going to want to leave. Likewise, OH minus is not a great leaving group. We've learned that from early ages. Water would be, and is the conjugate acid, and so, or the acid for this as being the conjugate base. So this is, and water is not an acid at all. So this is probably going to be number 2. This is the worst one, and this is probably going to be the next one. And then we've got something that would be acetic acid and H3O plus. And H3O plus is actually the strongest. It's the strongest acid out of this versus acetic acid, CH3COOH. And so this one will be the best leaving group. All right, so increasing reactivity as leaving groups, we want, says just we want the least first. That's going to be option 1, then we go to 2, which is the next one, then we go to acetic acid, and then we go to water being the leaving group. Hopefully that made sense to you. And then this question 5, a little bit tricky. You have to sort of increasing acidity of the hydrogen atoms. And really what I was testing over here is I wanted to see if you could recognize when a proton is acidic or not. And there was some, this question was actually a lot easier than you may have thought, because I only looked afterwards at the options available. There really was only one answer that makes sense to this. I mean, it's almost not even worth discussing the relative acidities of these different ones. We've got H there, this H, that H, and this one over there. If you just look at this, this is a proton which is next door to a carbonyl. Yes, it is relatively acidic, but its pKa is between 20 and 25. This is kind of like related to this one over here. I mean, it's if you recall, if we take away that H, we get the enolate, which is, of course, if it collapses and picks up an H, we end up with this over here. Which one is more stable? Well, this one is more stable, all right? Not the enol form. So it means that if this is the more stable one, then this H must be slightly more acidic than this one, because it's more readily given away, to get back to that. So these two are going to be very similar to each other, but this one being slightly more acidic. This one over here, these protons, if you remove that H with a base, you're going to end up with a minus on that carbon over there. You end up with a minus on that carbon. That minus can go nowhere. It can't be resonance stabilized or anything. This, for all intents and purposes, this H is one of the worst H's you can remove. Its pKa is going to be, I don't know, in the region of about 45 or 50. But this is a carboxylic acid. This must be the most acidic out of all of the H's. All right. If you read the question, it says place the following compounds in increasing acidity. Increasing acidity of the underlying hydrogens. In other words, the last one must be the most acidic. The last one has to be this one over here, which is number 2. If you look at the options, option D is the only one that ends off with a 2 in it. And so all the other options are just, they're not even options for this, this question. But regardless, forgetting about the way that I really kind of sillily didn't make it a bit more challenging in that respect, this one has to be the worst. So that's your worst. This one must be the best acid. And out of these two, we said that this one is less stable than this one. So therefore, this one must be slightly more acidic than this one over here. So we would go 1, 2, 3, and 4, like that. The last question was just something from first year. There were actually a number of you that got this right, and for that I was quite impressed. It talks about 3-hexene undergoing an ozonolysis. Use ozone and disulfide. So what happens? You're breaking the double bond and putting oxygens over there. All right. So we get 2 of those. The product is then reduced with sodium borohydride. Remember, NaBH4 4 sodium borohydride, and we end up with an alcohol. Okay, normally these are done in alcoholic solvents. So I'm just going to put methanol there just to make it complete. And then this was allowed to react in the presence of acid, HCl, with 3-methyl pentanoic acid. So it's pentanoic acid, 1, 2, 3, 4, 5. It's the acid, 1, 2, 3, 4, 5. 1, 2, 3 methyl pentanoic acid. We are combining this together, so please make sure that you can do the mechanism of this. I'm kind of treating this a bit like first years here. And we connect, and this is our product. Most of you kind of got that. Make sure you can do the mechanisms of that as well. All right. Okay, so that ends my first tutorial, and I will do the next one shortly as well. Cheers.